Okay, let's go ahead and get started. So thank you everyone for attending another iteration of our Clarify seminars. We have two complimentary talks today about simulation and kind of dealing with computational constraints in physics simulation. So first we have Irina Espejo from NYU talking about active learning for level set estimation and simulation-based inference. So thank you for being here, Irina, and I'll turn it over to you.
Thank you, Savannah, and thank you for having me. In this talk, we'll present Excursion, which is a tool that uses active learning to estimate level sets of expensive black box functions while optimizing costs. This is joint work with my collaborators, Kyle, Lucas, Gilles, Patrick, Eleni, Yannick, and Philip. Some of them have collaborated in the development of the tool, and with some others, I'm actually collaborating now for applications. So this is a high-level simplification of what a pipeline looks like for beyond the standard model searches. Usually, one of these searches ends up in a contour plot. This pipeline has, and then the goal of the researcher is to exclude as much parameter space for as many theories as possible. But this pipeline has several bottlenecks that limit these efforts to exclude parameter regions. And those are the bottlenecks that we want to tackle with this. First of all, there's the fact that there's a huge parameter space inside the possible beyond the standard models. Each of these theories has multiple parameters. And what we usually do in order to make it tractable is to constrain some of the parameters. So we fix some of these parameters and then try to make a contour plot with the rest. Another bottleneck is the event generation and the simulation. This step is very expensive, especially if we are running the full-blown detector simulation. So those two bottlenecks, and probably others, contribute to the fact that our contour plots are one-dimensional or two-dimensional. And what we want to do with Excursion is to scale these contour plots for higher dimensions. And we think active learning has some answers for that problem. Active learning is a technique, semi-supervised technique from machine learning, where the algorithm can interact with the data and the algorithm can query the oracle to level more data. So this type of problem appeared whenever in machine learning there were huge data sets, like for instance, pictures of dogs and cats that is unlabeled. A small percentage of this huge unlabeled data set is actually labeled. It has the tag dogs and cats. And then we know that the more images we get tagged, the better our models for instance, for classification will work. But labeling those images is expensive because you have to pay a human to do it, or like or an expert if the data is like more difficult than cats and dogs. So the way the pipeline works in active learning is in the form of a loop. We have a labeled data set, which is usually much smaller than the unlabeled data set. And with that, we train a model. With this model, we use it to evaluate over the unlabeled data set. So basically an interpolation over the data set. And we use this information to decide which is the next point that we are going to fit into the oracle to label. So which are the points that are worth our effort of using the oracle to label because we believe they are going to improve our model. So in high energy physics, the oracle is the simulation, is the simulator. And by labeling, we mean labeling by computing the CLS value for a particular parameter point. Once we have some of them, some of these parameter points labeled with the CLS values, then we will train a Gaussian process to interpolate over those that we don't have labels of it yet. And then we will make a selection over all of the rest of the candidates that are unlabeled, and then decide which is the one that we need to fit next to the simulator. This query selection, I'm gonna give more later. So we want to apply this loop to finding contours. This is the core in the left. There is the current approach, which is very expensive and consists on a regular grid. Ideally, what we would like to do is to only evaluate the simulator around the points that are close to the contour that we are trying to obtain. But we don't know where the contour is a priori. So excursion, this is when excursion comes in. We are going to have a trade-off between exploration and exploitation in order to have less evaluations than the ones that we will have on the grid and still estimate the contour plot. And so let's see how we do this. The statement of the problem is the following. We have a black box function that goes from parameters to confidence levels. The goal is to find the excursion set. So this parameter region that for a given threshold t, with as few queries as possible to the simulator. We start with some data set of points that we've already labeled. And then we train a Gaussian process. We find new hyperparameters conditioned on this data set that we have labeled. And then we use that to have a proxy for the black box function. This fit is going to play a role inside this function u, which is the acquisition function. The acquisition function is a scalar function that goes from parameters to a scalar, and it's cheap. It's cheap to evaluate. It's just a number. Well, it's cheap to evaluate, and it's what it's going to tell us is how worth it is to evaluate a certain parameter point. We are going to select the maximum of this acquisition function, and then how to construct acquisition function depends on your problem. And the maximum of it, we're going to take it and then feed it to the simulator. So I'm gonna put some 1D and 2D examples to understand this. Here in the first plot, you have a purple line. The purple line is, the threshold, and the dashed black line is the black box function, the true black box function. So then our goal is to find the intersection between the two. So basically, our goal would be to find this point, this point, this point, this point, and this point. The blue line is the mean prediction for the Gaussian process. And the blue shadows are the variance of the Gaussian process. This red line here means that we've evaluated at this point. At this, in this case, it's a one-dimensional parameter. So therefore, the Gaussian process is collapsing around there. Okay, and then below, we have the acquisition function that we are using in excursion, which is a combination of entropy. It's the entropy of the classification probability between being inside the threshold and being outside the threshold. But I can give more liters later. So this acquisition function in orange, we calculate for each of the candidates in the grid. And then we take the maximum, which is over here. Note that there is an asymptote in here, which is a point that we've already evaluated. And this means that it's completely worthless to evaluate a point that you've already run the simulation in. So this is a nice sanity check for this acquisition function. So now we evaluate at this point, that's plot number 2. And you can see that we have to refit the Gaussian process because we have updated our dataset. And then we can calculate again another acquisition function. Well, the same acquisition function, but using the updated fit. And we have a new maximum value, and then we are going to evaluate next at there, which is in 3, this red line over here. If we repeat this process multiple times, then we will arrive to a stage, that looks like this. This is one of the last stage of the problem. We've already found several um, level sets, several points in the level set. And now we have uncertainty around the threshold. So the acquisition function is, of course, going to be high there because it's worth it to evaluate at some point over here and then get more information about the function. So that's exactly what we do. And then when we do the we obtain with low uncertainty all of the points in the level set. And we also obtain a good fit of the black box functions, which was not the goal of the task, but they are closely related. So in 2 dimensions, this is an example in 2 dimensions, what the contour that we want to approximate is in dashed white line. And then the solid one is the one that it's our prediction. You can see that maximum, I run this experiment for 25 iterations. So there are maximum 25 points here being used. Compare these 25 points with the whole grid. So you can see that the grid is it's fine. And the performance is remarkable with a few points compared to the grid. We can perfectly model it. So we also expanded the excursion method to batches of points. For instance, instead of selecting what is the next point that we need to evaluate, what is the next batch of points, so that way we can take advantage of parallelization. And for a fixed simulator time, then if we run these batches in parallel, then we can obtain more information and have a better fit for the Gaussian process. We also implement multiple functions at the same time. So for instance, imagine that you have the same domain, same parameter space, but you want to approximate the expected contour exclusion, the expected exclusion limit and the observed exclusion limit, or you want to change the threshold. Instead of 95, you want 99 or something like that. We could also do that. And then, so we could select the points so that we estimate all of these levels that we are interested in at the same time. And we can also use multi-resolution simulators. And with this, I mean that imagine that we have one simulator that is lighter, but is more imprecise. And we have one simulator, another simulator that is heavier, but more precise. We can combine both of them to avoid running the heavy simulator as many times and only use it for fine tuning. So excursion is inspired by Bayesian optimization. In Bayesian optimization, the goal is to find the minimum and the minima and the maxima of a black box function. But this is significantly more difficult because we are not interested in points, but in regions. So we have to find sets. These plots show that this method can do better than a grid. These are four different experiments. And on the x-axis, you have the number of labeled points, so how many times we query the simulator. And on the e-axis, you have a measure for how good is the estimation of the level set. So in the y-axis, the lower, the better the estimation. So you can see that for the regular grid and the Latin hypercube, which is in blue and purple, they are consistently above that than our method, which is in green and pink. So basically, for the same computational cost, for the same amount of queries to the simulator, we get better precision with excursion than with what we would get with a regular grid. Now I'm going to talk about scalability because up until now I've only talked about 1 and 2D examples. So using Gaussian processes has drawbacks and has pros and cons. The pros are that they are very flexible, they are highly interpretable, which is something that neural nets lack. So we prefer to use Gaussian processes for that, but also the fitting can be expensive. Calculating the posterior given a data set can be expensive, especially if you start to scale it up with many points and in high dimensions. So there has been a huge effort in the community to improve the scalability. And one of these examples is GPyTorch. GPyTorch is a package that includes state-of-the-art fast posterior techniques to help improve the scalability of Gaussian processes. It has flexibility for priors kernels, exact versus approximate inference. There are kernels specifically designed to scale up a Gaussian process, a Gaussian regression. By They have native lazy tensor evaluation for big covariance matrices. Actually, they bypass when you have many data points and you want to calculate the posterior, you have to deal with big covariance matrices, or in high dimensions, the same thing. So they figured out a way to avoid the product and the composition of the covariance matrices by replacing this problem with an optimization problem, which is much faster. There are multitasking features that are very suitable for what we want to do. And the hyperparameter is very easy to do. And the hyperparameter tuning is easy to do thanks to Autorad. And there's also easy GPU support coming from PyTorch. So this has been key for starting to scale this algorithm. And lastly, I want to comment on a current project that we are working on, which is progressing well, which is applying excursion to the PMSSM analysis. So we are going to start we're going to start with this process that you have over here with five dimensions. So it's a mono HBB analysis with 5 parameters. And the way we are going to attack this, I mean, our goal is to find exclusion limits without having to constrain any of these parameters, or having to constrain them as low as in the smallest range as possible. And the way we are going to do this is that, first of all, we are going to construct a prior. And this is related to one of the drawbacks of Gaussian processes. So the better the prior that we have, the faster the convergence will be for the posterior of the Gaussian process. So first we construct a prior using recast. We're going to use past analysis, the past evaluation at the truth level, to construct a prior that will have encoded physical properties of this analysis, like continuity, smoothness, and so on. And this reinterpreting analysis comes from a dark Higgs boson analysis. And then we will apply excursion on top of that by querying the full-blown detector simulation, and we'll just only have to fine-tune with excursion there. So the main takeaway points from my talk are that we use smartly and amortizedly simulators to calculate level set estimation, level sets. And Gaussian process regression has pros, which is the flexibility and the conversion guarantees, but also has drawbacks regarding the scalability, and that's why we use GPyTorch to help overcome them. That's all I wanted to say for today. Thank you for attending, and if there are any questions, I'll be happy to answer them.
Great, thank you so much, Irina. Yeah, if there are any questions, I think feel free to just unmute yourself and ask.
Hi, Irina. This is Aishik. This was a really interesting talk. The question I had was, could you elaborate a bit more on, in one of the slides you mentioned that you could use a fast simulator and a full simulator to combine the information. Could you elaborate a bit more on how that would work?
Yeah. So imagine that you have two simulators, which I believe is the case at in high energy physics. You have one that maybe phenomenologists use, and another one that experimentalists use. And usually there's one that's more detailed about models the detector in a more detailed way, but it's also more heavy to run. It takes longer. So by multi-resolution, what we mean is that first we can use active learning, this excursion method, with the simulator with less resolution. So basically the one that is cheap and fast, but not that precise, to get an idea of how the black box function looks like. And that would be a prior for another round of applying excursion, but this time with the heavy simulator, so that we will already have a good prior, and then we would only need to fine tune the contour with the second step. Yeah, that would be the idea. I mean, do you want more details about how to do that, or sorry?
Yeah, this makes sense. So you use the fast simulator to build a prior. Yeah, that's very interesting. Thank you for your answer.
I guess I have a question, maybe about the geometric PyTorch stuff. Like how is everything implemented in geometric PyTorch now, or is that something you're still exploring? This is something that we've just like started trying to transition some of our work into from standard PyTorch.
Yeah, there's a lot of nice features already implemented, but I mean, for our work in excursion, we've had to do some extra coding and so on. But the core for the scalability comes from GPyTorch, comes from the kernels, and yeah, the specific kernels that they have implemented there that come from they are state of the art from recent machine learning conferences.
Yeah. Okay.
So you are looking to move your work to GPyTorch?
Yeah, well, so we have been doing like graph network stuff, and we started with just like standard PyTorch, but just like you mentioned, geometric PyTorch has like kind of standard message passing classes and everything already built in that are super optimized. So we are trying to move those studies into like GeoPyTorch, but we're having a few issues just with like, because they have this is kind of getting off topic of the seminar, but because I guess they have like optimized some of the message passing classes so much, it's not super transparent exactly what the math is in those layers, and so we're just trying to match it up like exactly to what we've been doing before. But yeah, it's a great library. Any other questions for Irina? Okay, well, thank you for your talk, and I guess we'll transition to the next talk. So we have Aishik Ghosh from UC Irvine talking about exploring deep generative models for simulation in Atlas. So thank you for being here, Aishik, and I'll turn it over to you.
Thank you very much for inviting me to give this talk. Thanks to Savannah. And okay, so this talk's gonna be about exploring deep generative models for fast simulation in Atlas. So a fair warning that it's a bit of a gritty talk about exploratory work where sometimes you have to take a step back to be able to take 2 steps forward. So I'll talk about the problems we faced and how we've tried to solve them. So I'll start with the motivation and the setup, and then talk about one particular problem, energy resolution problem that we had, and the model-centric versus data-centric solutions that we tried. And then taking a step back to figure out how we take a solution that we've built and scale it for the entire calorimeter of Atlas. And I'll finally conclude with some future outlook. The images on the right are representations of like cropped images of our calorimeter. So it's a 3D image, right? So we treat it as 4 layers, one behind the other, and each of them is a 2-dimensional image. So how does simulation work in Geon4? So Geon4 is our state-of-the-art detector simulator. And let's say you start with this photon over here. Once it interacts with the material, it might convert into 2 electrons, and one of the electrons might give another emit another photon, and then the process continues as the shower develops through the detector. But in the end, only the energy deposited in each cell is recorded. So this time evolution information is not recorded in our detector. So one legitimate question you might ask is there a way to go directly from the properties of the particle to the image? If we could do this, we would skip the time evolution and we could have some kind of a parameterized shower. And that way we could save a lot of CPU time. And why is CPU time important to us? For that, you can take a look at the plot on the right. So the black line shows the kind of CPU resources we expect to have over the coming years, whereas the blue dots are various scenarios of how much we might need depending on how much we can improve fast simulation and reconstruction algorithms in Atlas. So it does seem like we need to start relying much more on fast simulation techniques to be able to keep up with, make do with the resources that we have. And the pie chart at the bottom shows you the amount of wall clock time that's spent on each activity. Simulation takes up the largest chunk of that. And for Atlas, the calorimeter simulation takes up 75% of the Monte Carlo simulation time. So that's why this is the main focus, one of the main places that we want to optimize CPU usage. So ideally, the long-term goal for this project would be to be able to simulate particle showers orders of magnitude faster than Geon4. Also, to use much less memory compared to the current fast simulation methods, and also be less human time intensive and higher accuracy compared to the current fast simulation methods. So what are these current fast simulation methods? Atlas has had parameterized, hand-designed parameterized showers for over a decade now. And the upcoming upgrade, which is called the Fast CalSim V2, in fact, already incorporates various kinds of machine learning. So the way it's optimized is it's trained on Geon4 showers. These showers are generated for single energy points. So you have like 10,000 showers for 1 GeV and then 2 GeV and so on. And also the parameterization is segmented in different parts of the calorimeter. So you take this, the energy versus eta, which is the direction of the detector, and you slice that into grids, and you do the parameterization in each grid. And in each grid, you apply successive principal component analysis. You do longitudinal parameterization, lateral parameterization. There's quite a lot of work that goes in. And then during simulation, you want to bring all of this back together using interpolation mechanisms for the energy and so on. Yeah, it's a lot of work and quite an impressive amount of stuff that has to be done. And ideally, what we want to do is, in an unsupervised way, or can all of this, or alternatively do a variational autoencoder to automate all of this. Now, we're lucky to be able to borrow from a lot of experience of these fast simulation, the traditional fast simulation work that's been going on. For example, we have a list of variables that are like complex variables that we know we have to validate against to make sure that our network is doing what we think it's doing. And these are usually much more complicated than the simple physics variables that we can calculate standalone in Python. So they involve clustering algorithms and various kinds of corrections. Yeah, so the training data set we use to explore these ideas is borrowed from this traditional fast simulation approach, which means it's the data set isn't ideal for neural network training. For example, ideally we'd like the energy energy of the incident particles to be a continuous distribution, but instead we have only 9 energy points log space. So it goes 1, 2, 4, all the way to 262 GeV. So what we hope is to condition these generative models on the energy, and then hopefully it will also learn to interpolate correctly at intermediate energy points. And we'll see how it does a few slides later. The study was initially done in a small section of the calorimeter right near the center, the barrel region, which is the cleanest region to do the study. And then based on the results, we expand. And the initial studies was also done on just the 4 electromagnetic calorimeter layers, so 2D images and 4 of them to make a 3D block. Yeah. The 2 models we studied are the 2 most prominent generative algorithms out there right now. The first is the variational autoencoder. In case you aren't familiar, the idea is you have 2 stacked neural networks. The first is the encoder, which tries to take your training data set, in our case, the GEON4 single photon showers, and compress them into a latent space. And then the decoder takes this latent space information and tries to decode it back into the GEON4 data distribution. And the better it's able to reconstruct this, the better it is. And in addition, there's also some kind of a restriction put on the latent space. For example, we might require it to be Gaussian distributed. This is because eventually, once the training of these 2 networks is finished, we want to throw away the encoder and simply sample random noise from the latent space distribution, in this case, the Gaussian distribution, and inject these random numbers into the decoder with the hope that then the decoder will generate new data that comes from the underlying distribution of the training data set. The other algorithm we explore are called generative adversarial networks. Here too, you have 2 neural networks, the generator and the discriminator. The generator takes noise as input and transforms that into some kind of an image. And the discriminator does a usual classifying task of separating these fake generated images from the true GEON4 simulated images. And in the next iteration, the generator is tasked with fooling the discriminator, and it can do that by making the fake images look more and more realistic. So these 2 networks are trained iteratively, one to get the better of the other. And this way, we hope that once the training converges, the generated data will start to look very similar to the training data sets, and the distributions will match. Now, these GANs are quite popular, but they're famously very hard to train, and they're highly unstable. For example, they have a problem called mode collapse. So if you think of the image on the right as your target distribution, then so this is an average over several images. Then what happens is the generator might actually just produce images from one of these 8 modes instead of generating them from all of them in each training iteration. And as the cat and mouse game goes on between the generator and the discriminator, the generator just keeps moving from one mode to the other instead of capturing all the modes simultaneously. Another problem is that since it's not the usual classification training, there's no guarantee of convergence of this adversarial training. And also there are vanishing gradients sometimes, which means that the discriminator might just become too good, and then the generator is not able to figure out what kind of updates it should make on its weights to be able to better fool the discriminator. And over the years, there have been several propositions to fix these problems. So some people like to do mini batch discrimination. The general idea here is, apart from training the discriminator per event, you also give some information about batches of events to get some kind of a statistical property. And another strange idea is label smoothing. So instead of giving clear targets of 1 and 0, you might want to fuzzy it up a little bit. by giving 0.9 or something to try to get the discriminator not to be too confident. There's something called experienced replay. Then maybe you want to reverse the training every Fibonacci epoch, or use the feather of a peacock, some might say, from the first monsoon of the year. Well, of course, I'm joking about these things, but yeah, it really turns into something like an alchemy. And in case it wasn't clear from my tone, the last two are not real, but the others are. But one other idea that genuinely does work is to modify the loss function. And there are lots of papers about modified GAN training algorithms and loss functions that improve stabilization and convergence and so on. But it's very important to pick the right flavor because, for example, the BE GAN that I'm giving an example of here produces very realistic looking human faces, right? So there's good reason to be pleased with the results of this GAN, but the authors themselves admit that, for example, they see fewer older people in the generated distribution compared to the training data set, or more women than men. And what this means is that the generated distribution might produce very realistic looking faces, but it doesn't correctly model the entire statistical distribution. And in physics, that's what we want. So we should be careful about which flavor to pick. A flavor that I'm going to talk about is the Wasserstein GAN with the gradient penalty. It's the one we use in our studies. So in the Wasserstein GAN, the discriminator is replaced by what is called a critic. And instead of just trying to do a classification task, it tries to estimate the earth movers distance between the real and fake distribution. So the earth mover distance can be thought of as if you have two these kind of piles of some distribution, what is the minimum you have to move around small blocks to make one distribution look like the other one. So it's a statistical distance, and therefore it doesn't have vanishing gradients like the vanilla GAN. And in practice, it's implemented using this loss that I've written down here. So the first term, the Wasserstein distance, is just based on the output of the discriminator on the real and the fake images. But it also has the second term, the gradient penalty, which roughly penalizes the critic for making any sharp changes in its output for a small set of changes in the input. In the input. And since there are two losses, they're balanced using this lambda term, which is called the gradient penalty weight. The higher it is, the more the training algorithm will focus on the gradient penalty. And this will come back in a future slide. Now with this flavor of GANs, you have stable training, no vanishing gradients, and more often than not, there's no mode collapse. You also get more consistent results if you train multiple times with the different random seed. So you're happy about that. It's a bit slower to train than the regular GAN, but that's the price you pay. So this is very popular among physicists. If you look at a paper on how to GAN LHC events, so they're simulating full events, they use a Wasserstein GAN. There were 3 talks a few years ago about using Wasserstein GANs for the CMS future high granularity detector and a couple of other projects. The LHCb GAN also is a Wasserstein GAN. So you would think that we really stumbled upon the perfect flavor of GANs, right? The problem is solved. We can go ahead and simulate the calorimeter, Atlas calorimeter, but it's not quite that simple. We can see that stability doesn't really come for free. There's a cost you're paying. So here, this is the first plot I'm showing you of the GANs and the VAs trying to learn to reproduce the G4 distribution. At this stage, the GAN and the VAE were able to reproduce a lot of the other plots that I haven't shown you. I'm going to concentrate on the one that they both fail in. This is the energy response of the detector as a function of the incident particle energy. And the black is the G4, and the error bars you see are actually the standard deviation in each bin. And it's very important to get this standard deviation right. And we can see that the G4, the widths decrease as you go from left to right on this plot, whereas for both the GAN and the VAE, the widths don't decrease enough at high energy. And this is a serious problem. And we were also surprised by this because both the models get higher order correlations, right? But the total energy is just the sum of the pixels, and neither model is able to get this right. And an interesting comparison is that this kind of a feature, which is the sum of the pixel intensity, is not important in computer vision tasks, but it's very important in calorimetry. So it's understandable why this kind of a problem might not have shown up in any of the image simulation projects earlier. Now, what we thought is maybe the critic is having trouble learning this. So instead of just giving it real and fake images, and why don't we compute these physics variables of interest to us and help the critic learn to use these variables? Well, that doesn't help at all. It's because the critic doesn't have trouble learning a summation function. It's that the gradient penalty I talked about earlier prevents the critic from using it, because it needs a small change in each of the energies of the cells collectively becomes quite a large change, but the critic is prevented from making changes in its decision function based on small changes in individual cells, and that's the problem. But then the question is, do we abandon all the good things that the Wasserstein GAN gives us because of this one problem? Well, we're able to balance both the requirements. So we've come up with a slightly different architecture where we have two critics instead of just one. The first one does the same job as before. It looks at the entire image and tries to estimate the Wasserstein distance. But the second one only looks at the total energy. And with this, we lower the gradient penalty a lot, in fact, by 6 orders of magnitude. So it's able to make sharp decisions. And now, since we don't want to lose the stability of training, we only allow it to look at the total energy, not at the entire image. So the usual critic has a gradient penalty of 10, which is quite common in literature, whereas the e-critic or the energy critic has a much smaller gradient penalty, allowing it to really push the generator into producing right energy distributions. Right, and so with this, we're able to solve our earlier problem. We can see that the new GAN in green is able to mimic these the standard deviations quite well. And later on, we realized that these other physics projects that used Wasserstein GANs also encountered similar problems, and they solved it using different mechanisms. So one solution was to use maximum mean discrepancy loss on the mass in addition to the usual Wasserstein loss, which is very similar to what we're doing. So instead of using a neural network to estimate it, they computed by hand using inductive bias. And another project has used a post-processing network to do the first network generates the image and the second one just corrects for the energy. And an interesting discussion is also, like, authors of the big GAN, people from DeepMind, have even suggested that stability is overrated. In the end, we just need one model that simulates things well. So one might want to just use a vanilla GAN where it's not restricted by any penalties. And if the training goes unstable, you can just use tricks like going back a few epochs and training with a different random seed and so on. But we stick to the Wasserstein GAN for now because we don't have that kind of computing power to be training hundreds of GANs. But the next thing you might ask is, well, this solution seems very like Wasserstein GAN centric. So how do you solve the same problem for the variational autoencoder? That's true. The first one was very much a model-centric solution. Here, for the variational autoencoder, a lot of ideas were tried. So there were model-centric solutions like autoregressive flows to fix a latent representation. This is a typical solution that's often used to fix variational autoencoders. But also 10 times the training data set was also tried just to see if it's the data that's limiting the performance. In the end, the solution was quite interesting. It was actually the representation of the data. So the images were cropped with respect to the particle position in each layer instead, and the cells were normalized not with the total energy, but rather with the energy in each layer. So each layer was normalized differently. And also instead of having the usual reconstruction loss, the reconstruction loss for each cell was weighted by the variance in that cell, and that really improved the performance. You can see on the red distribution on the right now is able to have sharp widths much better than before. And the hard work paid off very well, because it was not just this distribution that the VAE learned to reproduce. It also improved in a lot of other distributions and started and outperforms the GAN in a lot of them, particularly at high energies. Now, beyond this, there was a lot of the Atlas geometry, calorimeter geometry is quite irregular, and we had to condition the GAN on these kind of things. So just to give an idea, if these yellow points are the position of the particle in the middle layer, because the cell granularity is different in each layer, you can have different kinds of alignment of the front layer cells with respect to the middle layer. So these are the 4 possible alignments that I've shown on the top. And on the bottom is a similar argument for the back layer, where the width in the eta direction is twice the size of the middle layer. And so there are 2 ways it could possibly align with the middle layer cell. And so there are eight combinations in total, which are encoded as a 2 hot vector, and the GAN is conditioned on these things. So that it's able to know that even if the shower looks the same, it's going to be recorded differently in the detector and should be able to reproduce this effect. Also, the GAN is conditioned on the position of the particle within the impact cell so that it can produce any edge effects. And with all of this, we're able to look at some high-level variables. So this is called the R phi, which is the amount of energy in a 3x3 over a 3x7 cluster in eta versus phi. And we see that the GAN not only reproduces the GN for the 16 and 32 GeV where it was trained, but also is able to interpolate at 25 GeV, even though the interpolation isn't trivial. So we're very happy about that these GANs and VAEs can interpolate. And just to have an idea of what the baseline looks like, on the top is the same variable for the upcoming upgrade to the traditional algorithm of fast CalorSim, where the algorithm had to be modified to make sure that these distributions look good there. Yeah, so we're happy about these distributions. Of course, we also tested extrapolation, and as we know, neural networks don't extrapolate well unless there's some good reason to think that they would, and in this case, they don't. Now, how do we integrate the neural networks into the Atlas C++ software? We don't want to install TensorFlow into the into the pipeline, so we use a package known as lightweight trained neural networks, which is based on the Boost package. And we've also upgraded the models for Onyx runtime. The advantage of Onyx runtime is that it supports custom layers out of the box, whereas for LWTNN, we had to add the switch activation function into the package so that it can be used inside the Atlas software. So Onyx would be the way we do things in the future. And the performance, we're very happy with the looking at the performance. So on the plot on the right gives you an idea of the order of magnitude idea of the kind of speeds for an individual shower in Geon4, which is the blue line, and it's a function of the energy of the incident photon versus what the neural network is doing, which is the flat line at the bottom. So the neural network takes about 70 milliseconds to generate a shower compared to tens of seconds for Geon4 or even higher at higher energy. And the actual neural network component takes less than a millisecond. The rest is just overhead that we could optimize, but we didn't because we were already sufficiently fast. The memory footprint is also very small, and we're very happy about that. So the parameterization file is about 10 megabytes for the network, compared to orders of a few gigabytes for the traditional fast simulation parameterization files. And the peak memory consumption, which can be a problem for fast simulation algorithms, and it's something we often have to keep in mind while developing fast simulation algorithms, is 1/3 that of for the neural network based simulation compared to the traditional method. And in fact, that 1/3 is also just the usual Atlas software that's taking most of the memory. The neural network itself is taking negligible memory. So the upshot is that the GAN and the VAE are as fast as they need to be and have a tiny memory footprint. So we're happy with the performance. Now we need to take a step back and think all the stuff we've developed is right now for a small region in the center of the calorimeter where everything is very clean. And we know that as soon as we extend to the hadronic calorimeter on the one hand, or further in the eta range on the other, there are going to be a lot more cells with different widths and granularity. And then the alignment that I talked about earlier, there will be even more combinations, and the combinatorics will explode. So we don't want to continue conditioning on all kinds of configurations. We will come up with a more scalable solution. And that's when we consider that even though real data is measured only at the cell level, GN4 can simulate data at point cloud level. So we could take advantage of that. So we could, instead of training on these cells, we could define these 3D virtual grids by hand and call them voxels, and train on these voxel level data sets. And another thing we can take advantage of copying from the fast simulation, the traditional algorithms for fast simulation, is to move from Cartesian coordinates to cylindrical coordinates in the direction of the incident particle. So that way you get the direction of the particle for free, and you've got this R versus angle dimension in which you can make your voxels. Yeah, and so doing that, another GAN was trained on this. So here, now we've moved from a small section in the center of the calorimeter to the entire calorimeter, including electronic and hadronic layers. And instead of just the photons, now we're looking at photons, electrons, pions. The architecture studied right now for this is the original, is the simple Wasserstein GAN, but maybe it can be again optimized like before. And for now, there are 300 GANs being trained for the 3 particles and various regions of the detector, but these are all things that can be optimized. So these are the first results for the photons. On the top, you can see the energy response is pretty nice. And on the bottom is the position response. We can see on the left that the position response in phi is not at all captured by the GAN, but the eta is not too bad. The phi is because the training data set has this simple geometry assumption that breaks down for the electromagnetic calorimeter. Now, if you look at pions, also the energy response on the top is decent, and on the bottom, the position response is pretty good. Which means that, like, currently this new iteration has trouble with photons, but is already impressive with pions. and now we can, apart from looking at single particle showers, we can start looking at full jet events. And so that's what we see in the next slide. Here again, the black is GN4 and the red is the GAN, and in blue is the current traditional fast simulation algorithm that we have. It's called Atlas Fast 2. And we can see that the GAN is already better at mimicking GN4 compared to the traditional algorithm. So there's a proposition to do something like a hybrid of simulating photons with the traditional method and maybe pions with the GAN, while we still continue improving the deep generative models. So then the next steps in terms of voxels is, of course, to improve voxelization and then go from these 300 GANs maybe to 3 or maybe 10 GANs and VA or VAEs. Incorporate all the machine learning lessons that we've already learned from the previous cell level studies into these voxel level studies, and move away from the simplified geometry so that the phi distribution in the electromagnetic calorimeter can be modeled correctly. But there's another approach we're also considering, which is to go fully point cloud. Instead of voxelizing the data set, there is an argument to be made to directly train on the sparse point cloud that's generated by Geant4, and this can be done with some kind of graph neural networks. And so I'm flashing a couple of images from a recent study that was done by Raghav Kansal and his collaborators on using graph neural networks for sparse point cloud simulation of in high energy physics. So we can see that they already get things like the jet mass and some typical variables pretty well. And it's and another thing we're considering is, do we want to introduce more inductive biases into the architecture? For example, the chronological evolution of the shower from one layer to another. If we can put that in the structure of the network, perhaps it'll improve results. We've already tried this at the cell level using dense layers, and it didn't work. But with these big graph neural networks, it might be an idea worth re-exploring. Just a few points to ponder about that I thought might be interesting to the audience here is, I've often been asked, why are you sticking to Geant4? Why don't you train directly on data? In our particular case, we don't want to do that because we know that Geant4 in some variable is not modeling the data correctly, but in Atlas, we have correction functions for this. And ideally, we want the fast simulation to just mimic Geant4 so that it can use the same correction functions and we don't have to develop separate ones. But it's true that, like, for example, if you want to train some generative model for hadronization, you might want to train directly on data. And another thing to wonder is if we do train a graph network for point cloud data, then this will not really have a lot of information about, it's not going to be super fine-tuned to the detector we're simulating. So we might wonder whether this can become a more of a general purpose model that you can switch out the calorimeter and train it again, and maybe it works on a new calorimeter. So kind of be detector agnostic in terms of architecture. Then there are some interesting discussions on, can GANs produce more data than the training data set? The answer is essentially no, but also yes, depends how you think about it. Yeah, and the biggest problem with generative models currently seems to be how to numerically quantify the performance of a generative model, which you can do easily for classification, but harder for generative models. Yeah, to conclude, there was a lot of work done in Atlas by 3 different groups to study deep generative models for fast simulation. The problem is to simulate the current irregular shaped Atlas calorimeter, which is slightly deformed compared to the idealized geometry. And so we need to correct for all of these things. The results in many cases are already comparable to the in development upgrade to the traditional fast simulation algorithm, which is all quite encouraging. And we hope to do even better in the coming months. We are exploring new ideas of improved voxelization for VAEs and GANs in point cloud generation with graph networks. And in fact, an interesting point to take home is there's no obvious reason to choose generally hard to train GANs over pretty fast to train variational autoencoders for any scientific applications. GANs seem to be far more popular, but in our studies, we didn't see any reason to pick one over the other. And finally, generative models inside Atlas have graduated from being a fringe idea to a mainstream discussion. So we're happy that we're making this kind of progress, and hopefully we'll continue making this progress. Yeah, thank you. And I'm happy to take any questions.
Great, thanks. Thank you. And yeah, if you have questions, feel free to just unmute yourself.
Hi, Aishik. Great talk. Thanks. So, if you simulate at the point cloud level, how do you go from the point cloud to the final detector response? Is that deterministic?
That's a very good question. So luckily, this is a problem that we don't have to deal with, because Atlas has been developing fast simulation for a while, and these the idea to take point cloud and then cast them into cells, these algorithms already exist, because fast simulation, traditional fast simulation algorithms are already generating at point cloud level, not at cell level. So we can probably take a function like that and modify it to our needs.
Cool, thanks.
I see David, you have your hand raised.
Yes, hi, Aishik, great talk. Can you say more about whether you can generate more showers with the GAN than it was trained with?
Okay,
I
yeah.
have never thought about it.
So it's a study. Let me put it back on full screen. I've actually linked the study done by I think it was this is a group in Heidelberg. They do this interesting study of they're able to show that the GAN produces more events in the end. It's because the GAN is able to it has some kind of internal regularization that keeps things smooth, so it's able to not overtrain on fluctuations. But in the end, so in that sense, it can produce more data than the training data set itself, by not learning the statistical fluctuations. But on the other hand, when you use the data for something, so you're doing it for a fit, then you already put inductive biases into the fit, right? You already have an idea of what the fit will look like. I mean, what the like it'll be a polynomial or whatever it is. And as soon as you do that, then you're also putting the inductive bias there. So they showed that the GAN will not give you more information than that's there in the training data set. So in the final fit, the training data set will give you a better result than the GAN. But yeah, so it's like a yes and no answer. But of course, in our case, like if we are training on 9 energy points and we're able to generate on like intermediate energy points, one might say that we're also generating more data than the training data set in that sense.
Okay.
Thank you. Any other questions? Okay, well, thank you again, Aishik and Irina, for your presentations today. They were both really interesting, and I appreciate you guys taking the time to talk with us. And I guess just a reminder, if you're not on the CLARIPHY mailing list, you can sign up for that through Google Groups. And we try to organize these kind of seminars fairly regularly. So hope that people will join us again. So thanks for joining, everyone. Have a good rest of your day.
Thank you very much. Bye.
Thanks. Bye.
Thank you.